Saurav Garg will be presenting SeqMatchNet, contrastive learning with sequence matching for place recognition and relocalization. Go ahead.
Hello, everyone. My name is Saurav Garg, and I'm going to talk about our paper SeqMatchNet, Contrastive Learning with Sequence Matching for Place Recognition and Relocalization. This work was done in collaboration with Madhu Venkadari from University of Oxford and Michael Milford and myself from QUT, Australia. So the research problem we are targeting here is the one associated with the question of where am I? And this is the question which has been asked by many protagonists from many different movies. And let's see if you can guess some of them right. Where am I? So I hope you got some of those correct. So the answer to that question is localization, where we want to estimate where we are with respect to some sort of a reference map. And one of the ways of doing that with vision-based information is to do visual place recognition. With visual place recognition, if given an image of a place, I can identify where I am because I'm revisiting that place. So that recognition gives me some coarse estimate of my location within that area. And a typical pipeline for visual place recognition looks like this. So there is an environment map. And with this environment map, it could be a topological or metric map, but typically it is a collection of several images of an environment. And given a query image, we want to then match it against all these reference images to localize this image. And there are two steps involved in this. One is data representation, where we have either local feature set or a global descriptor to represent that image. And then a data association step where we take this representation of query image, match it with all the representations of the reference database, and generate a match confidence. And with that, we're able to retrieve the best matching image or some top best match hypotheses. And given in robotics, we have access to spatiotemporal information. So we can often achieve this task with sequence-based information. So here, instead of a query image, we have a query sequence, and the data representation and association is then adapted accordingly. So what happens typically after this is once we have some sort of retrieval, either image retrieval or video retrieval done, we can then pass on our best matching hypotheses to structure-based methods where metric localization can then be done by using those techniques. And one of the main reasons why we want to use sequence-based information is to then solve these hard problems where because of scene appearance variations, it can be very hard to recognize a place by just using a single image. For example, these 4 images which are stitched together have been taken from the same place, but under very different conditions. And you can see that how appearance varies between day-night cycles and seasonal cycles, and it is hard to recognize a place. So in order to use sequential information with pre-existing single image-based systems, one of the ways to do that is to use a distance matrix, which is computed from single image-based matching. Here we can see we have reference images as rows and query images as columns, and each cell here represents some sort of a distance or score between a given pair of reference and query images. And with the help of sequential information, we can then search for matches within this matrix as one of the diagonals of this matrix. So this is how a typical distance matrix looks like. So here we have one method from 2007 where local alignment searching and spectral decomposition was used to to get rid of perceptual aliasing and then find accurate matches along the diagonals. Follow-up work looked at normalizing local scores within this distance matrix to then do a linear velocity search to then find matches within along the diagonal. And then one can also use odometry information, which is also often available with robots. And with the help of odometry information, one can then get rid of any kind of velocity variations so that all the warpings within this matrix, they become linear. And that makes the problem somewhat easier to solve. More recent methods have looked at graph-based search algorithms, where within any given local portion of a distance matrix, one can look for the actual path or search for the actual wall between the reference and the query sequence. Now, these being some of the representative approaches of the literature, but for more details, we can look at the literature review in the paper. But in all these methods, sequence matching never informs the single image representation learning. So all these methods apply a post-processing of sequence matching on top of existing single image-based systems. But there's never any kind of a feedback loop or an information loop from sequence matching to the single image representation learning. And this gap we then fill with our proposed method, SeqMatchNet. Here, what we do, we have triplets of sequences instead of having triplets of just single images. And these triplets, positive, anchor, and negatives, these can be derived from GPS-based supervision. This is something unlike existing methods where which use either time-based information to then do it in a self-supervised manner, for example, time contrastive networks. Here, with the help of GPS, we can exactly find what are the corresponding sequences and then supervise our contrastive learning framework. And the main contribution here is with the sequence matching-based triplet loss formulation, where we, instead of considering single images, we have a sequence of images which are represented as circles here. And the distance is computed as a diagonal of this matrix, which is computed through these two sequences. So this becomes the trace of this particular matrix. And the order is preserved, which means the T0 of first sequence is matched with T0 of the second sequence. And so similarly, T4 and T4. So by preserving this order, we are finding exact matches between corresponding elements of two sequences. With this, we compute our anchor positive distance, and similarly, we compute the anchor negative distance for given sequences. And then we use the standard formulation of max margin triplet loss, where we want to increase the margin between anchor positive and anchor negative. Now, what do we really achieve with this? So for this, we can look at some of the hard negatives, which are derived either from single matching, single image-based matching, for example, the orange setting here. And the other one, which is the blue one, where we're using sequence matching based negative mining. So considering these hard negatives, if we look at these scores along the diagonal of these matrices, so for the single based system, which is represented as an orange curve, vertical x is representing the negative distances. So we can see that at location T, the hardest negative is found at that particular location, not in its vicinity. And that is what the single image based system should do. We should find hardest negatives just at that location. But the problem with that is the elements in its vicinity are not going to be as hard. On the other hand, if we look at the sequence-based negative mining, we can see that even though the element at the location T is not the hardest one, but those in its vicinity are really hard. So overall, the sequence, so the elements retrieved through sequence-based negative mining, they're harder than those retrieved through single image-based negative mining. And that helps in learning better representations, which are guided by the sequence matching, which is the actual task during inference. In terms of the architecture, we use an image encoder, which is any kind of standard image to vector representation, for example, NetWLAD. And then on top of that, we put a fully connected layer. And this whole architecture only shares weights across all images. So each image is converted into a descriptor individually without doing any kind of descriptor aggregation. So the learnable parameters only remain in the fully connected layer as the weights for this image encoder are frozen. And then given the sequence matching triplet loss, we can then optimize for this single image descriptor through this fully connected layer to learn better single image representation. We also do negative mining online during the training. And with sequence matching as an additional aggregation of sequence scores, it adds on some computational burden. But then we come up with a new convolution-based sequence matching, which then makes it easier for us to do online negative mining. For this, what we do is we take an identity matrix as our 2D convolutional kernel, and then convolve it with the single image-based distance matrix. As you can see here, as this identity matrix will sweep across this single image-based distance matrix, it will compute the trace, which is our sequence matching metric or distance at that particular location, and that gives us all the sequence matching scores, to which we then mine the negatives. In terms of experiments, we considered 4 different data sets. And as you can see here, different pairs of images from different data sets, they show the level of appearance change, which makes the task harder. And we use a standard splitting regime where for each split for train, test, or validation, we have a unique reference and a query traverse. In this ablation study, we look at how training with just single images versus training with sequence matching helps improve performance. So we can see that if we use sequence matching for just the loss formulation or for the mining type, so whenever the sequence matching is involved, performance increases noticeably as compared to single image-based system. And this is done for both day-night, and this can be seen for both day-night and seasonal variations scenarios. We also compare against state-of-the-art techniques which use sequence information in few different ways. For example, sequential descriptors, where descriptors are aggregated instead of aggregating distances. And then sequence matching techniques, where either we use sequence matching on top of vanilla NetVira descriptors, or we use graph-based sequence search operations on given single image-based distance metrics. So in all these cases, we found that our method either performed similar to, or in most cases, better than the existing techniques. We also considered another ablation study where we looked at the effect of sequence length. And in this case, particularly when considering descriptor aggregation techniques, we found that for those descriptor aggregation techniques, using longer sequences typically makes them lose information as there's a reduction operation involved. So longer sequences lead to poor performance, but in our case, we're able to achieve a better performance with by looking at the max scores instead. So that's all from my side. And the source code is made publicly available. I'm happy to connect on LinkedIn and Twitter, and happy to take any questions. Thank you.
We just have time for one quick question before the break. Oh, there's a question up there.
Yep.
Can you wait for the mic, please?
Thank you for the very nice talk. It's really enjoyable. I wanted to ask if you thought about dealing with sequences with different frame rates, if the car goes slower or faster, maybe by using dynamic time warping in the loss formulation.
The question is for handling video sequences with different frame rates, or maybe cars moving different speeds. Have you considered using dynamic time warping in the loss formulation?
Yes, so that is definitely one of the things which we are looking into right now. So in this work, we simply considered GPS information to get rid of velocity variations. But yes, with the recent available methods, for example, either soft DDW or other techniques, we can definitely incorporate that, and that should hopefully make the system even better.
Thanks, Saurav.